All right, we should probably get started. A little bit late already. Okay. We're taking it a little easy today. It's Friday. Okay. You guys have a quiz today. It's actually already up, but you should wait until after class to take it, of course. So it'll be up until midnight or 11:59 p.m. just like usual. All right, and yeah, there's no help session today because there's usually very little demand for help sessions on the off week. Okay, PA6 is still not posted, so I'm sorry about that. I'll try to do that tonight. I've got it almost ready. Just need to kind of clean it up, and then it'll be up. So it'll be up sometime tonight, almost certainly. Okay. So let's see. I thought that we would do something a little fun today because, I haven't had time to prepare anything else, and so, and it's Friday, and we've covered a lot of material already, and so here today what I'll do is I'll show you the lambda calculus. Right? I've been kind of hinting at doing this. And I feel like, I'd be remiss if I didn't ever show you the lambda calculus and talk about it a little bit, right? It's very historically significant, and it really is kind of like the base computational substrate of functional programming languages. If they're all based on the lambda calculus, and even though our little Scheme 1 language is based on the lambda calculus, okay? So it'd be cool to look at it a little bit. But before we do that, I want to return to this little language that we were looking at before, right? We've spent the last few lectures looking at this little toy programming language here. And we looked at how you can go about proving progress. And then I haven't showed you proving preservation, but it's kind of a similar thing where you can do it by induction on the syntax, and it's just this kind of long and tedious process of making sure that everything works out. Okay, and so, but this is a language together with its small step semantics that we define and the type system as well that satisfies progress and preservation, so it's type safe. Okay, but then I mentioned that type safety doesn't imply that the programs always terminate. Okay, it doesn't imply normalization. That's another property. And it turns out that this language also has that property, but that any program in this language terminates after a finite number of steps. And I just want to kind of hint to you a sort of intuitive way, or one way to go about proving that would be pretty easy in this case, that doesn't always work. Okay, and really the idea is essentially so you can define a size function on expressions. Okay, you can define a size function in a really pretty straightforward way, and then just show that the step relation strictly decreases the size of expressions, so that every time an expression takes a step, its size decreases strictly. Okay, it goes down by 1 at least. Okay, and then if you can do that, that's sort of all you need to do. So. And so you could do that in a pretty straightforward way. Again, I kind of want to skip over it, but here we were talking about strong normalization. But suppose that you showed that. Suppose you have some size function, which we could define very easily. I could say, I don't know, like the size of a value is 1. Okay, and the size of a Boolean, I'll just write it like this, is 1. And the size of plus E1, E2 could probably just be size of E1 plus size of E2. Okay, you might want to add 1 there to be safe, but I don't think it's necessary. Okay, and so you could do something like this. And size of, again, it's pretty routine, if E1, E2, E3 equals size E1 plus size of E2 plus size of E3. Okay, whatever. And then you could prove, probably by induction on the syntax, something that looks, some proof kind of like for all E for all E and E prime, E steps to E prime implies that the size of E is strictly larger than the size of E prime. Okay, you could prove something like this, just that that every time you take a step, the size is strictly decreasing. Okay, and that would pretty much immediately give you the termination proof. And I mean, intuitively, you could think of it like suppose that you started with some E, and you had it, we'll call it E1, okay, and it steps to some E2, and that steps to some E3, and so on, okay? So suppose you have some trace of execution, just some sequence of steps that may or may not be infinitely long, okay? That's kind of the question here, is that suppose you have some trace of execution. Well, each one of these expressions has a size. So you could think that each one of these is mapped to some size by the size function. Okay, E2. Sorry, I'm trying to go quick here. Okay, and we know by that previous theorem that they're strictly decreasing. And each one is a natural number. They're strictly decreasing. And the size is always non-negative, right? By the way we've defined it. The smallest it could be is 1. Okay? And so, well, it turns out that the natural numbers have this property of being well-founded, which means that there are no infinite, strictly decreasing sequences of real numbers, right? That if you have a strictly decreasing sequence, sorry, I may have said real numbers. I mean natural numbers. If you have a strictly decreasing sequence of natural numbers, it must be finite, because eventually you'll hit 0 and you can't go anymore. Okay? So the idea here is that at some point, you bottom out. And there must be some term here that corresponds to that. Or let's use 1. Eventually you'd hit 1, and that corresponded to some term here, some expression with size 1. And the only expressions that have size 1 are the values, and values can't take a step. So you know that the execution must terminate there. Okay? And so basically this is a proof that any trace of execution is finite. And so this language has the strong normalization property. That's sort of an informal proof by picture, but this is pretty much the idea. Okay? But it gets interesting when this isn't true necessarily. That there do exist programming languages that have the strong normalization property, but for which the size is not always decreasing. Okay, so then it's a lot trickier. But in our case, it's easy. It's easy when you have some size function that's always decreasing. Okay, that makes it easy. Okay, so I just wanted to show that. And now we can get to the lambda calculus. Okay? Let me make a whole new thing here. Okay. So let's take a look. We're going to look at the untyped lambda calculus. Okay, and depending who you ask, they might prefer to call it unityped. Okay, if you want to be anal about that, okay, but it's usually called the untyped lambda calculus. Okay, and it's a very simple little programming language. So we'll start by writing the syntax. Okay, and it's going to be a language, and we'll call them terms instead of expressions. It doesn't really matter, okay? So I'll give a little grammar for the syntax of terms in the lambda calculus. Okay, so a term can be a variable, which I'll just write as x, okay? Variable. It can be a function. These are usually called abstractions. So it can be an abstraction that's written like this. We could just call them functions if we want. And it's just, lambda xt. It's like the sort of lambda functions that we've seen already. It's just there's a binder there for a formal parameter, and then the body, which itself is a term. Okay? That's called abstraction. And then there's application, which is just written like this. Just by juxtaposition of two terms. You say it's applying the left to the right, and that's function application. Okay? And that's it. That is the whole programming language, or at least the syntax of terms. Okay? So there's not much to it. It's essentially just functions, right? I mean, it's got variables and functions and function application. All right, and so it might be very surprising to you that, so this is the first programming language that was ever proven to be Turing complete, which means that, anything a Turing machine can do, the lambda calculus can do. And I suppose I could mention this. There's this thing called the Church-Turing thesis or hypothesis. What that says essentially is that Turing machines capture the notion of computability correctly. That if a problem can be solved by a Turing machine, that's essentially what it means that a problem can be solved by a computer in general. Right? The idea is that Turing machines are a kind of correct formalism for computation of like real-world computers. They capture what computers can do. Okay, so when something is Turing complete, that matters. That means something because that means that it can carry out sort of any kind of computation that any other computer can do, right? Okay, and well, this is named after Alonzo Church and Alan Turing. And Church was the creator of the lambda calculus. Turing was the creator of Turing machines. And together they proved that they were equivalent formalisms. They could do all the same things. So that's why I say that in the modern terminology, nowadays we call that proving that something is Turing complete to show that it's equivalent to Turing machines. So that's why this is like the first one to be proved Turing complete. Okay. Right. So we aren't totally done yet, because there's more to a language than just its syntax. So first off, I'll say, well, what are the values of the language? Okay, which of these terms do we consider to be values? And it's just abstractions. It's just the functions. Okay, so those are the values of the language. All right, and then we can give a small step semantics to show how do you execute programs in the language. And well, I mean, I don't know. I could write some example programs first, but let's do the semantics first, I suppose. So it'll be a small step semantics like we did before. So how are we going to do it? Well, when can a term take a step? Well, a variable doesn't take a step by itself, and an abstraction also is a value. So by itself, this can't take a step either. So the only kind of term that can take a step is going to be the application. That's where all the work happens. Okay, it's all about function application. So let's go ahead and do that. Yeah, so let's say we've got some T1, T2, and okay, let's make a congruence rule here. So here's our first congruence rule for application. So I'll call this E. So E app 1. So it's whenever you've got an application that looks like this, if the first, the left side can take a step, then we'll let it take a step. That's our congruence rule. Okay. And then we'll have a second congruence rule where I'll say, well, if the left one is already a value, then we can let the right side take a step. Okay, and we'll call this E app 2. All right. And then we'll have our computation rule, and that's really where the magic happens. Okay, so if you recall, the only values are abstractions. So I'll write it out as one. So you've got something like that on the left with a value, and you want it to step to something. Here's where you actually perform the computation. Okay. And well, we've seen this kind of thing before, doing function application. Of course, what we would do before is we'd have some environment. So we would take v2 and kind of map x to v2 in the environment, and then continue on with v1. But here, instead of using environments, we're just going to go with substitution semantics and say, well, let's just take v2 and substitute it in for x in the body of the function. So I'm not going to write, you have to be careful to define substitution correctly, capture avoiding substitution, but I'm not going to get into the weeds there. So let's just assume that we have a substitution operator that does what we want. So then all we do here is just perform the substitution. Okay, so the notation I'll use is to say, well, map x to v2 in the body. v1. Okay. E app. Okay, and that's it. So here's the entire small step semantics for the lambda calculus. Now we've already kind of chosen something here. We've decided on the evaluation strategy that we want to use, because you have more than one option there. But this is eager evaluation, right? We're saying, well, before you can do the function application, you have to evaluate the argument all the way to a value. Once it's a value, then you can substitute it in. Okay, so this is our eager evaluation strategy for the lambda calculus, and it's left to right. So I think that's sometimes called normal order, going left to right, but this is, eager or call by value. So this is the call by value. Call by value, small step, operational semantics for lambda calculus. Now if we wanted to make it lazy, that's another option. What would we do? Well, we would just delete this congruence rule completely for evaluating the argument. And then here we would, instead of v2, we could just let this be t2. Just let it be a term. And so then how do you evaluate an application? Well, you just evaluate the left side until it's a function, and then go ahead and do the substitution without even evaluating this. Okay. So that would be a way to change it to a lazy evaluation strategy. And it'd actually be even smaller. You'd only have two rules: one congruence and one computation rule. Okay. Now let's see. So of course it's fairly trivial to translate this into code, although you need to implement substitution. That's the hardest part. So I don't know if I'm going to do that. I mean, I have some pirate code that implements substitution already, so we could do that. But maybe I want to move on to something else. Okay. It can be kind of fun to program in the lambda calculus. Do you have a question?
Yeah. Can we see like a tiny example program? Because since we don't have values of numbers or booleans in this, I'm just struggling to see how you would actually make something happen.
Yeah. Okay. Yeah. So Well, one thing you can do is you can take this as your basis and sort of add some more things to it. You don't have to do that though. But that, that is one thing you could do. You could say, well, let's also add like numbers, or let's add booleans as like, another piece of syntax or something, and those would be like other kinds of values. But you don't need to do that, okay? And so it can be cool and interesting to look at how to program in lambda calculus without extending it at all, just because you don't need to. This is all you need technically, okay? And so the way to do that is to use what are called church encodings of the kind of familiar constructs that you'd be familiar with. Okay, and so we can do what we can do is look at some church encodings of stuff. All right, and let's see. I have a couple written down. All right. So the first thing we might want to do would be booleans. All right, so let's go down here. I'll start a new page. So this stuff is just kind of fun. Where are we at? Church encodings. Okay. Turns out you can encode all sorts of stuff. We can do booleans, we can do numbers, you can do lists, you can do pairs, trees, and that sort of thing. But we'll look at a few. So let's do booleans. Let's say that we want to come up with a lambda calculus term that encodes the boolean value true, and I'll write it like this. Okay. So how in the world could we do this? I mean, it has to be a function, right? Okay, so here I guess I'll just go ahead and write it out. Okay, so we'll make it a function. Right. Let's make it a function that really it takes two arguments. Okay, and we'll call it t and f. So here's a function that takes has a parameter called t, and then an inner function. So these are curried. So really, you could think of this as a function of two arguments, but it's curried. Okay, so it takes a true and a false. I'm kind of writing this wrong. I put the dots in the wrong spot. Lambda t, lambda false. Okay, and then it just returns the first one. It just returns. So it's a function that takes two arguments and returns the first one and ignores the second. So this is one way that we can encode a Boolean value true. Okay, this is a function that takes two arguments and returns the first. So then you could probably guess what false will be. Okay, so I'll go ahead and write it like this. Okay, it'll be very similar, but it'll return the second argument. All right. So here's our Boolean values. The church encodings of true and false as lambda terms. Okay. Now let's see. Once you have this, you can implement conditionals. Let's see. I don't have this one written down, but you could do like ITE would be what? Well, it takes a Boolean first, and then it takes like what will we call it? The left-hand side. I could call it like first, or I'll use A, I suppose. A and B. Oh, can't use B. All right, let's use first and second. First, second. Okay, so the idea here is that this should be a Boolean, and then if it's true, we should evaluate to the left side here, and if it's false, we should evaluate to the right, or like the next argument or the one after. So what do? Say B, F, S. Okay. Now I suppose I should be clear here that because application it only has two terms, right? So when you have BFS, what this really is, application associates to the left. So if you want to add the parentheses, it looks like that. So this is first take the Boolean, which will be one of these, and apply it to F for the true side, and then take that and apply it to S for the false side. And then if the Boolean was true, it'll give you back F, or if the Boolean was false, it'll give you back S. Okay, so you're letting the Boolean make the choice between the two things, between the first and second. But you usually don't have to write the parentheses. That's just what it means. So we're just taking the Boolean and applying it to the two sides and letting it choose Which one? Okay. So that's how you can implement a conditional using church encodings. Okay. And then there are some other operations you want to do on Booleans, like negation, conjunction, disjunction. So we can write some of those. So how about and? What will and be? Well, so the idea, and it should take two Booleans and produce a new Boolean, right? That implements their conjunction. So it'll take two Booleans, which I'll call B and C. Okay? And then somehow we should put a Boolean here that implements their conjunction. Okay, and how in the world could we do that? And well, one way to do it is it's kind of, it should be familiar to us from desugaring when we were implementing. If you recall, in our assignment, we were implementing Boolean conjunction using conditionals, right? And so we were using this kind of short-circuiting logic. So you could do something similar here. The idea is that, well, if Boolean is a function that chooses one of its arguments, then here, I'll just write it out, and then we'll take a look. Okay. So I'll just apply B to C and false. Okay. So what would happen here? Essentially, if B is true, then it'll pick the first one, and it'll give you C. And so then, if C is true, the whole thing is true, right? But if B was false, then it'll just sort of kind of skip C and give you false. Okay, so if you write out all the possibilities here, you'll find actually that this implements logical conjunction, or Boolean conjunction. Right, but it can be kind of hard to wrap your head around this stuff the first time. But again, remember what our Booleans do. If B is a Boolean, that means it's a function that you can pass two things to, and it'll give you one of them. If it's true, it gives you the first. If it's false, it gives you the second. Okay, so if B is false here, then you'll just get false back. That's what you want for and, right? If one of them is false, you want the whole thing to be false. Okay? But if B was true, then you need to know if C is true or not. So that's why, if it's true, it'll just give you C. And so then if C is true, the whole thing is true. Otherwise, the whole thing is false. Okay? And so then, if you remember what we did before in our homework when we were desugaring, then you might have a guess already for how to do this. Does anyone have an idea for how to do the disjunction? Yeah.
B, true, C.
Yep. Let's take a look. B, true, C. So it's a similar idea here. And if B is true, it'll just give you back true. And that's exactly what you want for OR. But if B was false, then you need to know if C is true or not. It'll just give you back C. Okay. So there's one more we can do, which is negation. So what should negation do? Well, it should take a single Boolean and then give you a Boolean back. So it'll take a single Boolean, and then we need to put a Boolean there. We need a function here that will be the opposite of B. Any ideas? Yeah?
Would it be B false true?
Yeah, that would work. So let's do this. All right, oops. B, false, true. Okay? And that's it. I mean, I guess it's pretty easy, right? So if B is true, you'll get back false. And if B is false, you'll get back true. And of course, each one of these things is itself, a function. It's a Boolean. So that's it. Okay? And so here are the Booleans. See, we can already do some Boolean programming just with functions. Yeah. Now, once we have Booleans, it's a pretty straightforward extension to do pairs. Okay? Pairs of values. So let's think about that. Okay? Still got plenty of time. So let's say we want a pairing function. Okay? So what pair should do is it should take two things and kind of build the pair of them. All right? So let's try this. Okay, so let's say, it takes the first and the second things. We don't really care what they are, but we're just building the pair that contains them. Okay, so now we want to put something here that should encode the pair of them. I haven't really said, how we're going about doing this. What's our strategy now? Like, what's the trick? With Booleans, it was making them functions that return, either the first or the second argument. So what's the trick for encoding a pair? Any ideas? You have an idea?
Composition maybe? That's not us.
What do you think?
I was gonna just say applied to S, but that's probably wrong.
Well, so yeah, we don't know what F and S is really necessarily. I guess you would be able to apply that to S, but that might not do what you want. You have no idea what that would do.
What about the set? That,
Well, we have no syntax for sets. It has to be a function here, right?
Okay, maybe it's like a function that takes a variable, and if it's one variable, it gives you the first one, if it's the other, it gives you the second. Like an ID kind of thing. So
That's-
if you give it 1, it gives you, or if you give it 0, it gives you the path. If you give it 1, it gives you the second.
That's pretty much it, right? The question is, how exactly do you implement that? And so, but that's pretty much the idea. So let's go ahead. What I'm going to do is say that it's a function that takes a Boolean and applies the Boolean to F and S. Okay, so yeah, you could give it false, and it'll give you the second one. And if you give it true, it'll give you the first. So it gives you a way of choosing between the two. Yeah. So when you say pair FS, now it's this thing that you can pass a Boolean to kind of project out the first or the second. So then that should kind of tell us how to implement the first and second projections. Okay, so if I write first, this should be something that takes a pair and pulls out the first element. But what do? We'll apply it to true. Okay, the second is going to do a similar thing. Okay, so now we have structured data in our lambda calculus. That it's kind of like having structs or record types or something where we can put things together. We can make pairs and then pull out the components if we want to compute with them. All right, so that's pretty cool. Okay, we've got Booleans and pairs. So then the next big thing would probably be numbers, right? So you're probably wondering, how in the world do you do numbers? So we'll keep it simple and only do natural numbers, to make it more manageable. Okay. But now, the question again is like, what's the trick? What's the insight for how do you encode numbers using functions? Yeah, you have an idea?
Or are we just going to do the successor like we did before, where we have a function that's like a pair of something, and you can either be 0 or the successor, and we have like however many applications of the successor function as the number.
Yes, it's going to be sort of like that, sort of like a unary encoding of natural numbers. But we're going to be doing it just, using abstractions in the lambda calculus. So it's not clear to me from your description how to translate that into a lambda term. Like, so what's the lambda term for 0? I mean, it's not a trivial thing to like think of how to do this. So here's what we'll do. So the idea is that these are called church numerals. So I guess I'll write that. So there's a special name for these natural numbers represented as lambda terms. And the idea, a church numeral is a function that takes a successor function and a 0 value and applies the successor function to the 0 value some number of times. And the number of times that it does that, that's the number. Okay? So what's 0 going to be? I'll write it as C0. Well, it takes a successor function and a 0 value and applies it 0 times. So it just returns back 0. So this is the idea. Okay, so now what's 1 going to be? C1. Well, I'll take successor and 0 and apply it once, right? So we could write out a whole bunch of these, and that's where you'd see your unary encoding here. It would be S of S of S. Okay?
And sorry, just for clarification, the Z is just a variable, right?
Yeah, I mean,
Okay.
it could be anything.
Okay, it could be also a function.
Yeah, well, it is going to be a function.
Okay.
It's not necessarily anything that corresponds to 0, but that's just the way that we're thinking about it here, right? Yeah, so that's the idea. So now we might want to define a successor function, actually, that takes any church numeral and turns it into the next one, okay? So what could that be? Say suck should take a church numeral, should take some number. I guess I'll call it n. So this is a numeral that has this kind of form, and we want to produce a new one that is one more than it. And we'll say, okay, well, if this has to be a numeral here, then we'll write it like the others. Okay? And then what? Well, you can go ahead and use n on S and Z. So this application here will go ahead and apply S to Z n times, and then you'll just put on another S to do it one more time. Like that. So here's our successor function. Okay? So now we can start doing some arithmetic stuff, okay? We can start defining more interesting things. Okay, so the obvious next one probably would be addition. We want to define addition. Call it plus. Okay, so plus should be, it should take 2 church numerals and produce one that's their sum. Okay, so it'll take m and n. But then what do we do? Well, I suppose we need to produce a new numeral here, so we could go ahead and put the S and Z. Say, okay, it's going to be a function that takes a successor and a Z, and then now does something with it. Basically, we want to apply S to Z m plus n times, right? So how could you do that? Might have to be kind of clever. You have an idea?
You would apply n to SD and then have m apply back m to n to
that sounded, I think, right, or very close to being right. So you say first do NSZ,
Yeah.
right?
And on the outside.
Yes, but M what? M can apply something to this.
Oh, the successor.
Yeah. Like this. Oops. Okay. So do we see what's going on here? So the idea is that first apply S to Z n times, and then apply S to that m times. So in the end, you've applied S to Z n plus m times. So that implements addition, right? So now, you know, this whole thing is a church numeral for m plus n. Pretty cool. Okay. So now, let's do multiplication. Got a few minutes left. Right, times. So times should take m and n, whoops, and multiply them. But now we can be a little cleaner. It may have even been possible to do that before. It probably was, actually, looking back. But there's a way to do this without writing out all of these, now that we have some other things to work with. Because if you recall, one of the ways to implement multiplication is by repeated addition. Right. So, and if you recall, what church numerals do is that they'll repeatedly apply a function to something. So I don't know if that gives you any ideas. Got one?
M plus nn. So you do m times the m. You would apply plus the n and m times.
It's very close, I think.
Oh, it would be from 0.
From 0, right. So here, I'll write it. So we're going to use m. Or you can do it either way, I suppose. And the function will be plus n. And we'll start it at 0. I think this is right. Okay, so if you think, what is plus n? This is actually, you know, we're doing this partial application trick. So we're partially applying it to one argument. So now it's a function that just takes something and adds n to it, right? So this is a function that is just like plus n. Add n to your input. And we're just going to repeatedly apply that starting from 0. So, you know, plus n, m times, starting from 0. That'll give you times. Now looking back, we probably could have done that here using our successor function. I'm thinking that we could have said something like, you know, m times applying the successor to n. Right? That would have worked. Pretty sure. Okay.
So could plus just be written m successor?
Let's see, how could we do plus? It'll take m, n, and then I'm thinking that you could do that. Does that make sense?
Does it have to have the C0?
No, so you'd actually be treating n as your 0 value. That's when you're starting from. And then your m times, you're just going to take its successor. There you go. So that would be a cleaner way. Okay, so, you know, you can do all sorts of stuff with this. We're running out of time, of course. But you could do POW, to like raise a number to a power. That one's pretty easy to do. I'll show you one more that's kind of neat. An is 0 check. Is 0. Okay? The idea here is that this should take some number, I'll call it m, and it'll give you a Boolean if the number is 0. Okay, well, it'll give you true if the number is 0 and false if it's not. Okay? So this can be kind of tricky to do, as of course we can't do like cases or anything. Okay, so I wonder.
Can we use our if then else?
You could, but then what would you put for the condition? I mean, this is something that you would use in an if then else if you were trying to, branch depending on whether a number is 0 or not. You say, if is 0 on the number, and so on. But how do you actually implement it as 0? Are there any ideas? Of course, there's a cute little trick for doing it, right? Just like all of these. So I'll write it out because we're running out of time. Okay, we're going to apply m because it's a church numeral. We're going to apply it to a function that just returns false and starting with true. Okay. So here, what happens? If m is 0, then it never applies this function and it just gives you true. But if m is anything other than 0, it will apply this function at least once, and so you end up getting false. Okay, so then that's how you can do is 0. All right.
That's kind of mind-blowing.
Well, okay, there's a lot more you can do, of course, okay, that we don't have time to do, and that I probably don't remember how to do, to be honest. But you can encode lists, of course, and we know since it's Turing complete that you could really do anything, but it's not guaranteed to be very easy to do or efficient or anything. This stuff is already very inefficient. Okay, but yeah, so we're out of time. So I just thought that so I'm never going to ask you to program in the lambda calculus, but you should know what it is, and you should understand the idea, right? Of this, you should know the syntax, okay, and the semantics, and maybe so you can add on a type system. And there's more interesting stuff that I kind of forgot. We don't have time to do today, but you can also do recursion in this language, and it's not immediately obvious how in the world you would do that. Okay, so
I thought we were using recursion when we did multiplication. We used plus.
No, because plus is already defined by the time you're doing this. So this is not a recursive occurrence because plus is already defined, and plus didn't have to refer to itself. Right? So if you remember, recursion is self-reference. That would be if times appeared here when we're defining it. Okay, we're out of time. Let's see if we have a quiz. Oops. Oh, yeah, that didn't work. Okay, so we might do a little bit more with lambda calculus next time because it is actually illustrative, and it'll be useful to understand something that comes up in our Scheme 1 language. All right, let's see if we have a quiz. Okay. All right, so see you next week.